Hello and welcome to section 21.3, three-dimensional work and energy. In this video we'll be going over example 1, which looks at how to calculate the kinetic energy of a 3D rigid body. This is that example. It's a disc and a rod rotating about the vertical bar, which we say is the z-axis. I've redrawn that over here. So before we can proceed, we need to write out what are the equations for kinetic energy. So we'll start off about the center of mass, G. So the generic equation is T equal to 1/2 mass velocity of center of gravity squared. This is a scalar, so just the magnitude of it, plus 1/2 omega, the vector, dotted with our angular momentum, hg. If we choose axes that are principal axes, so x, y, and z, basically making our products of inertia go to 0, then we can simplify this even further. So 1/2 mass velocity of the center of gravity squared plus, in more traditional form, 1/2 I omega squared. And we're going to do that for each coordinate. So x, y, oops, forgot my 1/2, and z. So this looks a lot more like what you saw with planar rigid bodies. Now, if I have a fixed point, it could just be momentarily fixed. It could just be some kind of instantaneous 0. Or it could be permanently fixed due to like being pinned or rigidly connected or something. So we're going to use O, kind of indicate 0 velocity. You could also say fixed point 0. Well, then what happens is we get T equal to, so we don't have a velocity that we care about, and it's just the rotation that we analyze in this case. So 1/2 omega dotted with h, about that fixed axis or point. And again, if we have some principal axes, x, y, z, where our products of inertia go to 0, then we can expand this out, which is 1/2, and then x, y, z. So ix omega x squared plus 1/2 iy omega y squared, and then 1/2 iz omega z squared. So for our problem, this whole thing is rotating about this z axis. I would like to use this fixed point, or in this case fixed line. So I want to make it so that everything is rotating about this line, if I can. There are other ways to do this. Center of mass is not going to be very preferable though. So I'm going to rewrite this equation. So our T will be 1/2 Ix omega x squared plus 1/2 Iy omega y squared plus 1/2 Iz omega z squared. And from our problem here, we only have omega z, and we know that this is a cone type problem. So this is our instantaneous axis, so our axis of rotation. So I will have no rotations in the x or the y. So I will get a 0 here and a 0 here. So this problem will simplify down to T equal to 1/2 Iz omega z squared. So my challenge becomes, we know this is 5, finding Iz. So the mass moment of inertia of this thing about this z-axis. So we're going to start off by making it a little bit easier. So I'm going to draw it over here to the side, just as a 2D thing. So we're going to make an axis that comes out this way. We'll call this z prime, and then I will have a y prime, and then I'll have an x prime coming out of the page. Roll x into y, you get your z, so we're in good shape there. So x is out of the page. This, and then our z is right here, and so we'll find what that is here in a second. So I have 90 degrees here. This is 200. This is 100. If I do a bit of trig, I can find this angle, which is also this angle. We can call this theta. So theta is tan inverse of opposite, which is our 100, over our adjacent, which is 200. We find that theta, when you plug it into your calculator, will be 26.57 degrees, rounded to 4 sig figs here. And then if we need our hypotenuse, we can find that as well. It is 223.6 using Pythagorean theorem. Alright, so we're going to use this because our shapes is probably get a little lost here. So this is our disc, this is our rod. So that's our shape. So we would like to just calculate each of those just using the basic shapes in the back of your book. Hopefully you can see. So again, if I kind of draw the, so if I drew a top view of this thing, and I put my center point right here, I'll have, say, a y-axis out, well, I'll just put y up and x over to the side. You can see, oops, you can't see that because I have to push the page up. You can see that we have in this xy plane, if I put this in the center, which it is, then this is symmetric. That means that ixy is 0. Our product of inertia is 0. And then we've done this in previous examples where I can take some shape like this, where I have my z and I have my y. And I can find the IYZ for each of these two shapes and then move them to a point, a common point. And because I'm not going to move up or down off of this Z, I'm going to also get that YZ is going to be 0 due to symmetry. And the same picture will be used for IXZ. So all my products in this case are 0, which is really nice. So that means we only need to find our IY. Well, actually, we don't even have to find IY. We don't need IY. We only have to find well, actually we do. Because what we're going to have is we're going to do our rotation. So we're going to find IZ as IX prime times the cosine of alpha squared. Or I guess you could say cosine squared alpha would probably be the way you'd actually write that. Cosine squared alpha plus IY prime cosine squared beta plus IZ prime cosine squared gamma. And then you would keep going normally, but we've already shown that our products are 0, so I don't add those terms on. So this is that equation of moving things to a different axis. So I'm moving it from this z prime over to my z, as was given to us. So alpha will be 90 degrees. So x is straight out of the page. So straight out of the page, and it'll still be straight out of the page when I rotate. So it's just going to be it's then going to be 90 degrees over to our new z-axis. Our z beta and gamma. Alright, and then for beta and gamma, let's just redraw this y-axis up here, where it actually makes more sense to look at it. So we have our y-axis and our original y-axis. So to get over to here, our y-axis is going to go basically 90 degrees minus this angle. So this will be 90 minus the angle that we found, which was 26.57. And then our gamma will go this way, and that'll be the 26.57. I'm going to put it in as negative. Alright, and this becomes, just a second, 63.43 degrees. Alright, so we have all our angles. We need to get IX, IY, and IZ. Actually, we don't even need IX because cosine of 90 degrees is 0. So I actually don't even need this one. Kind of looking ahead. So I just need to get IY and IZ. So IY. So remember, these are going to be about these prime axes, so about this axis and about this axis. So for the z-axis, this is a slender rod. It will have no inertia about the axis it's on. So it's just the disk. So IZ for our disk will be 1/2 mass radius squared. So 1/2, its mass is 7 kilograms. And its radius is 100 millimeters. We're going to put this in as meters, so 0.1 squared. When you run that calculation, you will get 0.035. For the, that is also just IZ, period. For IY, which also happens to be IX, by the way, we don't need IX. We're going to do the about the endpoint for the rod, and then we're going to do the disk about its center and then move it. So we're going to use parallel axis on that. So we're going to get I rod about its endpoint plus I disk plus mass distance squared. So parallel axis theorem. Let me move that up so you can see that. So for the rod, we will get 1/3 ml squared. So its mass is 1.5 kilograms. Its length, it is a 200 millimeter, so 0.2 squared. For the disk, again, this is not about its axis of rotation. This is about one of its, kind of like think about a quarter. So it's not the normal spinning axis. It's the axis like this. So it'll be 1/4 ml squared. It'll actually be just half of this number. 1/4 7 0.1 squared, and then its mass again is 7, and its distance is going to be moving this 200. So 0.2 squared. When you put all that together, you will get a 0.3175 as our numbers. So at this point, I'm going to move all of this into our equation to get IZ. I'll move that on the back, and I'll be right back. Alright, so we've transferred the numbers to the back here. This is our original equation. We've just plugged in all of our numbers, so IX and IY were both 0.3175. IZ prime was 0.035. Put in our angles that we found, did our calculations, and we get 0.09152 for IZ. So it's about the actual z-axis as it was drawn in the problem. So if we bring back our equation, we know that T is 1/2 IX omega x squared plus 1/2 IY omega y squared plus 1/2 IZ omega z squared. We established that omega x and omega y were 0 because we have an instantaneous axis of rotation here. So this just becomes 1/2 0.09152, the number we just found, goes there, and then our omega z is our 5 squared. You plug that into a calculator and you will get 1.144 joules of energy. So again, just recapping, we had a cone, space cone, whatever, rotating about the z-axis, which meant that we had an axis of rotation about here. Chose to use the point up here at the end as our point O. So we use the fixed point O equation, which is this. Because we have everything about the z-axis, this term goes away and this term goes away, and we're left with just this. However, to find the mass moment of inertia about this axis, we ended up making a translated coordinate system, so z prime and y prime, with x still being out of the page. Did some trig to find the angle between the things so that we could find alpha, beta, gamma to this z-axis from our z prime, from our y prime, and from our x prime. And then proceeded to use our mass moment of inertia translation from a z prime to a z. And so remember, this equation has 3 other terms, but they're all for our products of inertia, which are 0 due to symmetry. Put them together and solved. Hopefully that helps. If you have any questions, feel free to reach out.